Good morning, everybody. So basically, I want to start today's lesson kind of recapping what we talked about yesterday. So if you have a small p-value, what that means is the probability of the data you got happening purely randomly by chance is so tiny that we can actually reject our null and say, hey, we actually have convincing evidence that what we thought was true is true, because the probability of the data we got by chance is so small that it's like, I think we might be right. Versus if the p-value is large, we fail to reject the null because while we might have some evidence, it's not what's called convincing evidence. It's not enough for us to say, hey, the statistic that is already out there is completely false and we should throw it away because I surveyed 50 people and they disagreed, right? So sometimes it may be preferable to use a different boundary line, like 0.01 or 0.10 when drawing a conclusion. So like when I say the p-value is small versus large, what is the cutoff factor, right? Is it a probability of 1%, 5%, 10%? Okay, so by the end of this lesson, we're going to talk about the different percentages and why one might be used over the other. So a significance level is the value that we use as a cutoff to decide if an observed result is unlikely to happen by chance alone. So it's kind of our cutoff value for whether it's small, like a small p-value or a large p-value. So if our p-value is smaller than our cutoff point, that's when we would say the p-value is small. Therefore, we can reject the null because we have convincing evidence that what we think is true is true. But if the p-value is bigger than that significance level or that cutoff point, then we fail to reject the null because we might have some evidence, but we don't have convincing evidence to throw away the initial claim. So here's an example. Go ahead and read through it real quick, pause the video, and unpause it when you're ready to hear the answers. All right, so we've got our null and our alternative. I'm going to switch to a pen here. So the null is that the mean battery life is 30 hours, right? And we're saying, actually, I think that this new AAA battery actually lasts longer than 30 hours, right? So this is the stat that's already out there. This is the one we're trying to test. This is the one we're saying, I think it lasts longer. So basically, we then take some data and we get a sample mean of 33.9, which seems to kind of prove our alternative. But how do we know if it proves it or if it's just like, oh, just by chance we could have got some really good batteries that day, okay? So we end up getting a p-value, and you don't know how to calculate the p-value yet. That's coming. We got to really focus on what these things mean first, okay? So they just give you that the p-value is this, okay? That is a probability, you guys. So when I say p-value, it's like a probability. So I could also change that to a percentage and make that 7.29%. So that means there is a 7.29% chance that purely randomly, we ended up getting a number larger than 30 when we took a sample. So what conclusion would you make for each of the following levels? So this first significance level is kind of like 10%. This bottom one is like 5%. So if we're saying our cutoff point is 10%, well then technically this is smaller than the 10%. So we would, if you go back to this last slide, p-value is less than the significance level, so we would reject the null. Meaning, this number happening purely by chance is only 7.29%. Since that's lower than the 10% cutoff that was chosen, we can reject the null and say, hey, we have convincing evidence that we're right. However, if you use a 5% cutoff, we would fail to reject the null because the p-value is actually bigger than 5%. Okay, the way you kind of tell which one to use, you guys, 0.05 or 5% really is used 9 times out of 10 across the board in statistics, but also in other areas, other fields. So like if you're taking AP Bio, for example, you'll see a cutoff point of 5% a lot. If you're in psychology, you'll see 5% a lot. You might use 10% if maybe it's not a big deal. Like maybe the data you're talking about is, I mean, really, AAA batteries, if you're a little off on what those are, like who cares? It's not a big deal. So 10% isn't as big of a deal. If you use a significance value of 1%, that's usually for things like medicine. You don't want to say or disprove someone's statistics on a particular drug, for example, because, oh, well, you got a 10% chance of it happening purely by chance, so okay, we're good. So 1% is usually a little bit more strict, so they use it for things like medicine, because you don't want to just claim that some doctor has no idea what they're talking about unless you really have evidence that, hey, your drug doesn't work anymore. This new one does, okay? All right, so there's kind of the way we would word the solutions if you want to pause the video and read through it. That's like the fancy wording for it, and you'll see some of that same wording on your assignment today. Okay, this last part right here, you guys, I'm going to tell you this right now. If you are done after probability and stats, you do not need to panic about type 1 and type 2. Really, it's not a big deal and it's not a huge concept, okay? So if you get stuck on what these different errors are, please don't panic. If you're planning on taking AP stats next year, it does come up a little bit more in AP stats, but again, we cover it again, so it's not too big of a deal. Basically, what the errors are is a type 1 error occurs if the test rejects the null, but the null is actually true. And a type 2 error is if the test fails to reject when the alternative is true. Basically, these two errors happen when we get data, we say, nope, the null's false, my new information is better, and then it's like, oh, actually I was wrong. And it doesn't happen very often, but it can. And it's really hard to remember which one's which. So what I like to use is this little figure right here, where if you reject the null, like your data rejects the null, but actually in the real world, that null hypothesis is still true, that's a type 1 error. Versus if you failed to reject the null, but actually, so that basically says like the null is true, but when actuality, your alternative that you came up with is true, that's a type 2 error. The way I tell the difference, you guys, if you don't have this table in front of you, and which you can while you're doing your homework, but the way I remember it is fail to type 2. So if you fail to reject the null, that's a type 2 error. Okay, so that's kind of how I remember that. I want to skip that section. Okay, so here we go. So during, basically we've got a null hypothesis that the probability or the proportion is 60.63, so 63% of customers had to wait longer than 2 minutes. And we're saying that we think less than 63% of customers waited longer than 2 minutes. That's our alternative. And we picked a higher significance level because really, if we're wrong, is it that big of a deal? No. Okay. If we were talking about, like I said before, like medication or something that is like life-threatening, we might want to use a lower significance level. But if we're wrong on this one, who really cares? Like, oh no, more customers had to wait. Like, I think we'll be all right. So describe a type 1 error and a type 2 error. So remember, fail to type 2. So a type 2 error, I always start with that one because of the fail to type 2. Let's say the manager doesn't find convincing evidence that the true proportion of drive-through customers who have to wait longer than 2 minutes has decreased, when it really is less than 0.63. So we fail to reject the null when actually the alternative is actually true. Well, really, is that big of a deal, right? Like we say, no, it's exactly 63% when actually it's less. I mean, that's not a huge deal, but it's kind of a bummer for the manager because the manager would like to be able to prove that his customers are waiting less than 2 minutes, right? Versus a type 1 error, the manager does find convincing evidence that it's decreased from 63% when it actually still is 63%. So that's more like, okay, he finds evidence like, no, my customers wait less than 2 minutes, 63% is too high. And he goes and tells his boss, and his boss believes him when actually it is still 63%. Both errors, again, not a huge deal, right? They're not a big deal. And so when you ask yourself, like, which one's more serious, would you rather, like, be wrong that it decreased and it actually is still 63%? Or would you rather say, oh, 63% of our customers wait 2 minutes or more when actually it's less? Like, I'd rather have this error personally because, right, like, I think this could lead to upset customers, which might decrease sales. But this one, for example, maybe if the manager's lying to his boss, right? So it's one of those weird things, like both errors are kind of bad in their own way, and based on the situation, you can try to tell which one is worse. So here's another example. Oh, for the battery example that we talked about before, those AAA batteries. So give a consequence of each type of error in this setting. So if we had a type 1 error dealing with those AAA batteries, the company spends more money to produce the new batteries when they actually aren't any better than the older, cheaper type. Okay, that's kind of a big deal. If I were running that company, I wouldn't want to spend money creating a new battery because I have data that says it lasts longer when really the one I'm creating before that's way cheaper to make is just fine. So that's right, spending more money is kind of a big deal. If it were a type 2 error, maybe the company doesn't produce the new batteries even though they do last longer. So maybe the new batteries, even though they do last longer, we find evidence that they're about the same and we go, nah, we're not going to produce that. Really, that's not that big of a deal. So which one's more serious? Definitely type 1. Spending money and we don't need to, right? Versus type 2, hey, we don't make a new battery that lasts longer. I think we'll survive. It's okay, right? That's kind of the idea. All right, so actually, I apologize. You do not need to worry about this slide as I'm looking at it. This is not something we worry about too much, so no worries there. What I want you guys to do, though, is now that you're done looking at the video, try to do homework number 1. Really, it's okay if you're using the answer key a lot for this first homework assignment. It's okay. I want you to really try to wrap your head around why these things make sense. I know you don't know how to find p-values. You don't know how to set up the situation or where some of these numbers are coming from. But this first assignment is getting you guys to think about, okay, given these numbers, what can I say about the situation? Okay. Then we will move into next week where I'll actually show you guys where some of these numbers come from, how they're calculated, that sort of thing. But you need to have the big picture kind of wrapped around your brain before I start throwing weird numbers and things like that at you. Okay. Don't forget, if you're stuck or if there's still something I need to try to explain in a better way, stop by and see me for office hours so that I can try to help. Okay. Enjoy, after you're done with your homework, enjoy your weekend, and I will see you guys again on Monday.